Hey there, Chem Squad! Today we're going to look at electron configurations again, but this time with a twist. This time we're going to look at transition metal ions. So there's something a little bit different about these particular transition metals. Most transition metals have those d orbitals that seem to get in the way because they're so big and large. But you know what? We have a different method for electron configurations, specifically for these transition metals. So let's get started with some of the more common ones that we have known. So, for example, let's start with Cu. We know that these guys have a very specific promotion that happens. Okay, they're from that special copper family where if we take an electron from the s orbital, okay, we can give it to the d orbital. So in this case here, normally it's 4s2 3d9, but we take one electron from the s orbital and we promote it to the d orbital to give us 10. So I usually kind of just show it like this. Okay, so that we have one electron being taken from a lower energy level orbital and promoting it to a higher energy level orbital. But that's fine for copper. Okay? But what happens when copper loses electrons? Okay? Well, copper is one of those multivalent atoms, okay? Meaning that it can actually become copper 2+ or copper plus. Because it has multiple configurations here, okay, in terms of it losing electrons, here we see a loss of 2 electrons, and here we see a loss of 1 electron. Now, in the past, you mostly would take the electrons away from the outermost valence shell. It's not the case for transition metals, because they have to be a little bit difficult. Transition metals, you see, they tend to lose the electrons from the s orbital first before taking from the d's. So they lose electrons from the s orbital before losing from the d. And this makes sense because if you lose electrons from the d orbitals, it's because they're larger, they destabilize much more. So instead, you want to try and lose it from a smaller orbital first, and then lose it from the d if necessary. So what that means is, for copper 2+, we have this as the original electron configuration. Okay. But now we're saying that because we're losing 2 electrons, okay, we're going to get rid of this electron here. That'll be 4s0. And then because we need to lose another one, this will become 3d9. Now, you're kind of wondering, well, what does this give us? Like, weren't they happy to just have 10 electrons in the d orbitals? Yes and no. I mean, copper has more than one charge, okay, meaning that it can be stable as long as there's something else to, stabilize them. So in nature, when this happens, this is the natural state of copper 2+. Now, copper 2+ ions, as we can see, have their d orbitals partially full. It's not completely full, and it's not completely empty, but it's partially full. And what we can take from this now is this particular arrangement will give us colored precipitates. Okay. So copper 2 plus forms colored precipitates, which I'm going to abbreviate with PPT. Okay, so it's a solid substance that actually has some color to it when it reacts with other substances. So most of the time, these copper 2 plus ions, okay, they'll react with something like, let's say, sulfate or chloride, and the crystals themselves will give them basically what they need in order to be stable. But at the same time, these precipitates all seem to have color, okay, especially when they're partially filled. In contrast, let's take a look at what happens with Cu+. Oops. Cu+ loses only one electron. But again, the trend is for us to lose the electrons from the s orbitals first. So because it loses a single electron, I'm going to take an electron from s, so that electron's gone. We're not promoting anything, it's just been removed. Okay, so there must have been enough ionization energy in order for it to lose that one electron. But when it loses that one electron, we notice that the d orbital remains full. So it's completely full. What we notice as a response to this is that when Cu+ forms precipitates, they form precipitates that have no color. Okay, so no color. Okay. In the chemistry world, when there's no color, that precipitate just looks white. And that's the trend that we kind of see. We see that almost all transition metal ions that form precipitates with color have partially filled d orbitals, while all transition metals that either have completely empty d orbitals or fully completed d orbitals, they give you a white color or no color at all. So let's summarize. Switch colors again. Transition metals lose electrons from the outermost s orbitals first. Okay. Once you've taken all the s orbital electrons, okay, then they will proceed to the d's. So when losing electrons from d, we see two patterns. if the orbital ends in a d1 to d9, the precipitates have color. So precipitates of transition metals. I don't know why I keep putting an S on transitions. Precipitate of transition metals have color. But after losing electrons from the d orbitals, if the ending of each orbital is either d0 or d10, then the precipitates have no color, or at least they show no color. They just appear white. So you guys are going to conduct a little lab activity in the future regarding this phenomenon. We'll give you a bunch of transition metal ions, and we will get you to basically reacting with other chemicals to form precipitates. And then you're going to analyze whether those precipitates have color or not. Once you figure out where they have color or not, you're going to compare it to their electron configurations and determine whether or not our little patterns are true or not. Okay? So for the time being, there's a couple of ones that I would like you to try out. Okay? I want you to predict whether or not these two here show color or not. So we'll just say try these. I want you to write out the electron configuration of Sc3+, and I want you to write out the electron configuration of Cr3+, and predict which ones, if any of them, would actually have colored precipitates. And I will basically take this up the next time I see you in class. Good luck, guys. Thank you.